Hi Dr. Rosita, I'm Vignesh from TMNV company. So first of all, I would like to start the video by explaining about the material balance of crystallizer, separator and also dryer. So first is this is a crystallizer with the efficiency of 94% and there's a 3 different stream, 1 input and 2 different output. So since the efficiency is 94%, so the water out, this stream will be 94% of water in. And the stream is consists of water, sucrose, impurities and also reducing sugar at a total flow rate of 359,331.139 kg per hour. Next is the separator with 3 different output, 3 different stream, 1 input and 2 different output. With the efficiency is the 99.8%. So means 99.8% of sucrose will be transport at the 22 stream and balance 0.2% will be molasses. So actually the molasses include all the components with different mass fraction. Next is the dryer. Dryer, there's 4 different stream. One is the input and one is the output, and this stream, both 24 and 26 stream, is the hot dry air. So 24 is the hot dry air, 26 is the wet dry air, which is include dry air and also water. And this dryer is the efficiency of this dryer is 94%. I also want to continue with the boiler. So the boiler, there's a water in at 25 degrees Celsius and steam is getting out at 332 degrees Celsius. So we increase the temperature by using the energy from the bagasse, where we burn the bagasse and we consume the energy from that to increase the temperature. So the burned bagasse will be getting out as a fuel gas. The steam that getting out from the boiler will not use all the steam to the evaporator. So we just use a certain amount of steam to the evaporator. The excess will be stored at the generator. So based on the reference, the net calorific value of a boiler is the 7,671 kJ per kg. So since we got the degree Celsius and also the specific enthalpy from the table, so we interpolate to find out the specific enthalpy at 332 degrees Celsius. So mass of bagasse, whereas the mass of bagasse is getting from the bagasse that getting out from the extractor, clarifier and also from other process. So we're using Q equals to M delta H. So the delta H we already get it from here. The Q we find out from here. So the Q is actually M, this M mass of bagasse times with net calorific value. So we get Q at kg per hour. If you want to change to kilowatt also can. So we find out the mass of water by dividing the Q with delta H. So we get the mass of water required is the 4,442,502.65 kg per hour. So we know that steam out is the same as the water in. So steam out is the 4,442,502.65 kg per hour, and the steam in evaporator is we getting this value is we get it from the evaporator, and we just substitute this value with this value, so we get the excess one. Remaining will be stored at the generator.
Okay, good morning, Dr. Rosita. I'm Tan Wei En, and today I'll be talking about washer. Okay, for washer, we will assume that kinetic energy and potential energy is equal to 0, as well as Q, because there's no change in temperature in washer. So we just take account of workshop, which is 3 kilowatt. Okay. And then the same thing happened here in shredder. 0 for kinetic energy and also potential energy. And we just take account of our work shaft, which is 0.03056 kilowatt. And then now we move on to extractor. for extractor, there's a temperature change, which is inlet 68.7 degrees Celsius and outlet 70.8 degrees Celsius. Okay, we will take the inlet as our reference, which is 68.7 degrees Celsius. So as reference date, H cap will be 0. And then for output, we calculate using integrate the CP value. So after doing our calculation, we will have 18,000 kilowatt for extractor. So now we'll see our clarifier. For clarifier, there's three different parts. Okay, for the first part is in a liming tank. For liming tank, we will take using the methods of heat of formation method, we will obtain 476,000 kilowatt, while the second part is reactive. The second part is reactive process, which is we will use the delta H formation as well, heat of formation method to do our delta H calculation, and we obtain negative 460,000 kilowatt. Okay, and the last part is a non-reactive part, and we will have 65,000 kilowatt using the integrated CP method to obtain our delta H in the non-reacting process. Okay, so total up the three parts of the delta H we got. So we have 81,000 kilowatt.
Assalamualaikum, Dr. Zita. So now I'm going to discuss about the energy balance around the filtration unit first. So in order to find the delta H around the filtration unit, we use the formula of delta pressure divided by the density of the solution, and we get this value, and then we multiply this value with the mass flow rate and divide it by 3,600 to get 578.1858878 kilowatts. Next is evaporator. So as you can see here, the temperature is 128 to 62.7 degrees Celsius. So first we set a reference state of water, liquid, sucrose impurities and reducing sugar at 128 degrees Celsius, and water vapor at 123 degrees Celsius. So the delta H we get is negative 222,470,702.1 kilowatts. So next is crystallizer. As you can see here, the temperature inlet is 93 degrees C, and the outlet stream for the first outlet stream is 89 degrees Celsius, and the second outlet stream is 60 degrees Celsius. So first we set the reference state of water at 25 degrees C, while sucrose impurities and reducing sugar at 93 degrees Celsius. So then we calculate the delta H of the unit, where we get negative 7,259.10859 kilowatts. So next is separator, and the temperature inlet is 89 degrees C, and the temperature outlet of the first stream is 60 degrees C, while the second outlet stream is 53.6 degrees Celsius. So first we set the reference state of water at 25 degrees C, while sucrose impurities and reducing sugar at 89 degrees Celsius. So then we calculate the delta H, which is we get this value, and then in order to calculate the Q, we add the delta H with the work shaft of the machine, where we get the final value of negative 11,913.32876 kilowatts. So lastly is dryer. So as you can see here, the temperature of the inlet stream is 60 for the first inlet stream and 70 for the second inlet stream. And the temperature of the outlet stream for the first one is 60 degrees Celsius, and the second outlet stream is 60 degrees Celsius. So first we set the reference state of dry air and water at 25 degrees C, while sucrose impurities and reducing sugar at 60 degrees Celsius. So first we calculate the delta H, where we get 194.824687 kilowatts. And in order to calculate the Q, we add the delta H with the work shaft, where we get the final value of 198.824687 kilowatts. So that's all from me. Thank you, doctor. So for pumps, delta H equal to the H cap, where H cap equal to the specific volume times with the pressure change. So first we assume that the specific volume of the solution equals to the specific volume of the most available component in the solution. So therefore we get the final value of delta H equal to 173,296.9 kilowatts. So for the second pump, you also assume that the specific volume of the solution equals to the cap of water, So we get the final value of Q equal to 599,919 kilowatts. So for the third pumps, first we assume that the specific volume of the solution equal to the V cap of the specific volume of water, where we get to calculate the Q of final equal to 493,310.8 kilowatts. So for the fourth pump, it's also the same thing where we get the Q equals to 438,953.77 kilowatts. And for the fifth pump, uh, we assume that the specific volume of the solution equal to specific volume of sucrose. So the Q equals to 5,231.699 kilowatts. So thank you for listening. Hello, Dr. Rosita. So for heater 1, we use it to increase the temperature from 27 degrees Celsius to 68.7 degrees Celsius. So first we set the reference state of all the components at 27 degrees C. Then we get to calculate the delta H equals to 92,719.79134 kilowatts. So for the second heater, we use it to increase the temperature from 79 degrees Celsius to 90 degrees Celsius. So then we set the reference state of all the components at 79 degrees Celsius. Therefore, we can calculate the delta H equal to 92,817.59088 kilowatts. So for the third heater, we use it to increase the temperature from 90 degrees C to 128 degrees Celsius. So first we set the reference state of water, sucrose, solid, and everything else at 90 degrees Celsius. Therefore, we get to calculate the delta H, where we get 320,640.7264 kilowatts. So for the last heater, we use it to increase the temperature from 62.7 degrees Celsius and to 93 degrees Celsius. So first we set the reference state of water and the rest at 62.7 degrees Celsius. So we get to calculate the delta H equal to 10,188.372 at 6 kilowatts.
Okay, so now I'll be talking about energy balance in our heat exchanger. The purpose of heat exchanger is using the Q in flow gas to increase the temperature of dry air in from 25 degrees Celsius to 70 degrees Celsius. Okay, so from our table B8 we use, then we will obtain the H cap value for air is 1.524 in 70 degrees Celsius after doing the extrapolation. So the delta H here, the Q for heat exchanger will be Q equals to delta H. The delta H, after we calculate, we will have delta H NH out minus NH in, will obtain 256.514 kilowatt. That is the energy needed for temperature to increase from 25 degrees Celsius to 70 degrees Celsius. And now we'll take a look at the total energy balance for the whole process. After taking all the energies here, and we times by the number of equipment which the needed, and we will obtain the energy. The total energy needed is exothermic. The total process is exothermic, which means it will release 1.4 billion kilowatt throughout the process. That's all. Thank you.
Okay, now I'm gonna explain about the costing. So this is the table. So this one is a column for the equipments. Price. This one is a price for each equipments. Quantity. So the quantity is based on the flow rate output or flow rate for the machine. Cost is the multiply of the quantity and also price. And the total equipment cost is the 94,959,276 ringgit 24 cents. So this is the total equipment cost, and 5% is for the freight and transport, and equipment cost at the site is the addition of these two. Length factor for solid is a times with the 3.89, which is actually ISBL cost. OSBL cost is the 40% of the ISBL cost. Design and engineering is at 20% of ISBL plus with the OSBL. Contingency is the 10% of ISBL plus with the OSBL. Total fixed capital cost is the ISBL plus with the OSBL plus with the D and E, which is design and engineering, and also contingency, which is X. Estimated working capital is 50% of the total fixed capital cost. Total investment that required throughout the process is the total fixed capital cost and also estimate working capital. Now we go to the operating cost. There's 4 different parts. First is the variable cost of raw material, which is sugar beet, utilities, which is water, maintenance for the machine, and then also last but not least the capital charges. Then we go to the cash flow diagram. So there is a end of year, total capital cost, production rate, price sale, operating cost, revenue, cash flow, and also cumulative cash flow. So we can see the cumulative cash flow for the first 2 years. So for the first 2 years, we got negative value, which means we are in loss for the first 2 years. But at the end of end of third year, we already get our profit. So for this cumulative cash flow, we can plot it in graph. So easy for us to see it. So this is the graph, project cash flow diagram. This is the cumulative cash flow, and this is the end of year. So for the first 2 years, we are in loss. That's why the graph is going downwards. But at the end of third year, we already achieved our profit. And when go on from third year to beyond that, so we will get our profit proportionally or linearly. So that's why the cumulative cash flow is directly proportional to the end of year when when we start from the year. So that's all from me. Thank you so much, doctor, for lending your ears and time to watch our video. Thank you.